All right, you asked for it, so here it is. You want to know how to price all this stuff? This is part 1 of 3. Hold on your hats because we're going to get into option pricing again. We're going to use the black model with some changes. So hold on. It's stuff we've already done. It's just a matter of the simple logic. We're going to exchange some data in the black model. I'll explain this the best I can. And my suggestion is you're going to want to study the next 3 sessions repeatedly in order to figure this out if swaptions are your thing. So with that being said, let's take a look here. Swaption valuation before expiration. We now show that a swaption can be understood as a portfolio of calls or puts on SOFR. We have seen that the payoff expiration for a call and a put on SOFR is given by equations 1910 and 1911. Call equals payer swaption, put equals receiver swaption. We know notationally that this is the structure. Equation 1910 gives the payoff for a call on SOFR, while equation 1911 gives the payoff for a put on SOFR. The payoff for a payer swaption, equation 22.25, has the same form as the payoff for a call on SOFR, equation 1910. Similarly, the payoff for a receiver swaption, equation 22.28, has the same form as the payoff of the form of equation 22.25 or 1910 for each swap payment date. Similarly, a receiver swaption consists of one payoff of the form of equation 22.28 or 1911 for each swap payment date. Therefore, a payer swaption is a portfolio of calls on SOFR, while a receiver swaption is a portfolio of puts on SOFR. We've seen that the black model could be used to value options on SOFR, assuming the SOFR rate at the expiration if the option is log normally distributed. In pricing a swaption, we apply the identical technique to value each call or put that pertains to a single payment on the swaption, and that together constitute the value of a payer or receiver option. We first focus on a single payment on a swap that underlies a swaption. Assume that the swaption is being valued at time t and that the option expires at time t. We consider the nth payment on the swap, which occurs at time t of n, which occurs sometime after t. Thus, at the time the swaption is being valued, the swaption has time t, cap t, minus t remaining until the expiration, and time t of n minus t remaining until the nth payment on the swap. The difference between the time to expiration and the time until the payment is received is important for pricing. For example, in pricing calls and puts on SOFR, we took account the fact that payments are determined in advance and paid in arrears. This required taking into account the full amount of time from the present value date until the time the payment is actually received. Keeping in mind the distinction between t minus t and t of n minus t, the values of the call and put pertaining to a single payment on the swap are as the call price equals notional principal times FRAC, which is partial time a year. And this is our discounting of our SFR and our DISA 1 and DISA 2. And the same, we're going to just exchange in order to do the put. And then we have our normal DISA 1, DISA 2. As equation 22 shows, the DISA 1 and DISA 2 terms use the time period t minus t. This time period pertains to the expiration on the swaption, which determines the probability that the swaption will finish in the money. That's critical. By contrast, the discounting runs over the period t of n minus t of t because this is the time from the valuation date to the payment of the underlying swap. Because the swaption is simply a portfolio of calls or puts, the value of a payer swaption is simply a portfolio of calls of the form of equation 22.3 And a receiver swaption is a similar portfolio right here. We've seen this in other applications. We're just moving things around a little bit. If the logic is a little bit screwy, go way back to the very beginning of options, make a bit of an investment, and review this stuff. And here we have DISA 1 and DISA 2 are as described in equation 22.3. T is the valuation date, and T of N is the time at which the nth payment will be received. Up here, okay? We have T of N minus T, T of N minus T. The notation can be a little screwy, compliments of Excel. But with that being said, in addition to using the continuous discounting at a constant rate of equation 22.31, we can also value the option using zero coupon factors that reflect the shape of the term structure. So here we have pair swaption and notes the changes. We're not dealing with this time factor. We're dealing with the strike rate and the SFR. Work through these, okay? And I'm going to go into the numbers next. That's what you've been waiting for. Brad Williams, Frugal Finance. Thanks for watching.